Alright, Physics 11H, we're going to look at worksheet 3. Unit 3, worksheet 5, angled forces. Alright, so we've started dealing with this already, the idea of forces balancing each other out, figuring out quantitative amounts of force, and so on. So this first problem is just get your brain going and figuring out, like, okay, if this much force is pulling up, if this much force is pulling down, is it balanced? Or what would I have to do to make it balanced? So number 1 says determine the magnitude and direction of the forces required to balance the following situations. Sketch the missing forces with a vector and label them. Diagrams not to scale. I tried to make them to scale, but I put that disclaimer in there because there's always somebody who's trying to look extra close and nitpick on whether or not it's perfect. Right? So we have a positive 6 Newton force, positive 6, and then negative 4 newtons. Positive 6 newtons, negative 4 newtons. So to balance this, you'd have to add another negative 2 newtons. And how do you draw it? Well, you just kind of try to draw it next to it, maybe in a different color pen, something like that. So that gives me a total force of 0 newtons acting at that point. 6 newtons up, we say F net. F net means total force or sum of the forces. And actually, we call that the y-axis. We'd actually call that F net y, the total force in the vertical direction, the y-axis, along the y-axis. F net y, sum of the forces. In this case, F net y would be positive 6 newtons, minus 2 newtons, minus 4 newtons. That equals total of 0 newtons. All right. Let's look at the one that's. Let's look at the next one here. Not the next one. I'm going to look at the middle one on the bottom. We have a positive 8 Newton force going this way, and a positive 12 Newton force going that way. So what would balance these out? Well, simply a negative 12 Newton force that way and a negative 8 Newton force this way. In this case, you'd say F net X would equal plus 12 newtons minus 12 newtons would equal 0 newtons. And you would say F net Y, the total force in the Y direction, equals positive 8 newtons minus negative 8 newtons, minus 8 newtons. It's actually kind of, if you think about it, really, if you're saying it to sum of the force, it's probably better to say it's plus 8 newtons plus negative 8 newtons equals 0, if that makes sense. I don't know. So that's all you're doing. See what you can figure out there. Now, you might be able to imagine this, right? And this last one we just did. Figure out the rest of them. Well, could you balance out that 8 and 12 Newton force with only one other force? Right? Could you say, okay, I have a plus 8 Newton forces up, and I have a 12 Newton force going to the right. Is there any way to balance it out with one single force? The answer is yes. It would have to be something kind of going that way, right? And the way you figure that out is you make a parallelogram out of your two force vectors. You make a rectangle, and whatever the diagonal of that rectangle is, that's what we call the resultant. And whatever that is, the resultant of those two forces, if you make a force exactly opposite that, it'll balance everything out. Now, how do you figure out how big that force should be and what angle should it be at? Well, that's what we're going to learn. Turns out we use trig. I know that's a bad word for many people, but it's not that big a deal. If you find the hypotenuse of this triangle, that'll be what the resultant of these two forces is. So 8 Newton height, 12 Newton base, you use Pythagorean's theorem, find the length of this line. That tells us the resultant of these two vectors. This one would have to be that as well. The angle, well, you'd have to figure out what this angle is, and then translate it over to this triangle here. More on that later. Don't worry about that too much right now. All right, so let's take a look at problem 2. At least get it started here and see what's going on. A box with about 50 kilograms of books in it is on the ground with a rope tied to it. A mover is trying to pull the box along the ground but can't get it to move because of the heavy weight and the amount of friction. The mover is pulling the rope with a 300 Newton force at around a 30-degree angle with respect to the ground. Draw a force diagram for the forces acting on the box. So this dot represents the box. All right, we did force diagrams. We have the force of the earth pulling the box down. That's Fg. We have the force of the ground supporting the box. That's Fn. We have this person pulling on the box, right? That's the force of the rope on the box. We call that force of tension. Ft is the force of the rope on the box. All right? And then it says there's friction, right? So there must be friction holding it in place. So those are our 4 forces. Well, we're going to put these 4 forces on an axis. Keep things straight. On what we call a coordinate system. Coordinate system consists of an origin and some sort of reference direction. That's a positive x direction. That's the positive y direction. And so on. This angle says is 30 degrees. All right. Now, the next question. Is all of the mover's 300 Newton applied force, this force of tension, going into trying to move the box to the right in the positive x direction? How can you tell? Well, no, that force is not all going in the positive x direction. It's also going in the positive y direction. That force of tension is pulling up and to the right. The rope is pulling the box up a little bit and to the right. If the person got down low and pulled it horizontally, then it would only be pulling to the right. So you can tell it's not all going to x direction because the rope is angled. The rope is angled. So therefore it's also pulling up. Can you think of a way to figure out how much of the mover's force is going into his attempt to move the box? All right. So, turns out when you draw force vector diagrams, they're to scale. The length of that arrow is to scale. So let me just draw that arrow off to the side here. So if I say that force is equal to 300 newtons, I could draw this 30 centimeters long, and that would be proportional to the force at an angle of 30 degrees, right? 30 degrees. It turns out if you make a right triangle of this, right? The width, so this is the force, right? The length of the base of this triangle represents what we call the x component of the force. The x component of the force. It's actually the projection of the force down onto the x-axis. The height of this triangle we made here is the y component. Okay, we say that's the x component of the force. This is the y component of the force. Alright? And actually, technically, the y component you should draw over here. You kind of make like a parallelogram out of this. You actually don't draw the y force there. It actually should be over here. Fy. My bad. Alright. So you make a rectangle out of it. The height of that rectangle represents the y component of the force. The width of that rectangle represents the x component of the force. They don't literally add up to 300. They add up to 300 via Pythagorean's theorem. Alright? So, if I figure out the length of this base, that's going to tell me how much this force is pulling horizontally. If I can figure out how much it's pulling up, then I know how much its y component is. Alright? If I can figure out the length of the height, I can figure out how much it's pulling up. Sorry. Okay. So let's figure out this x component. Well, the length of the base of the triangle, we use SOHCAHTOA. SOHCAH and TOA. So, ka, this is going to be ka, right? Cosine of 30 equals adjacent, which is fx. The adjacent side is fx. I'm going to erase this for simplicity's sake so we can see what's going on. The x component of the force divided by the hypotenuse, divided by 300. So the x component of the force is equal to 300 newtons times the cos of 30, which is equal to 260 newtons. All right, so this rope pulls to the right with a force of positive 260 newtons. So that's how we figure out what's happening here horizontally. That's how much force is pulling to the right. Where's the rest of the mover's applied force going to for part D? Well, it's going up in the y direction. Oh, so it must be 40. Nope, wrong. It's not 40. They just don't add. They add via Pythagorean's theorem. All right? So what must the total force in the horizontal direction add up to? Write an equation showing how the forces acting in, or the components acting in, the x direction add together. Well, all right. So what we do here is we usually draw the components right on the force diagram with dashed lines or a different color pen or something like that. All right, so ftx is the x component of this force. fty is the y component of this force. How do they add together? Well, ftx and fty, they must add up to 0. Whatever's going on there, or sorry, ftx, not ftx and ft. ftx and the force of friction must add up to 0. They must balance each other out. All right. So how strong must friction be to hold the block in place? How do you know? Well, if we know ftx is 260 newtons, the amount of force that the rope's pulling horizontally, and it's not moving, right? They must add up to 0. Well, the force of friction has to be equal to negative 260 newtons, right? This has to be, we know this one is 260, positive 260. This has to be negative 260 to balance everything out. All right, so the force of friction has to be 260 newtons. We know it because it's got to balance out what's trying to pull it forward because it's stationary. It's locked in place. Whatever's pulling it forward, friction is resisting. 260 newtons are pulling it forward. Friction must be 260 newtons. All right. How about the vertical direction now? We haven't done that yet. So let's figure out what that Fy is, what the height of this triangle is, how much it's pulling up. So to find the height of this part, which is the same as the length of this vector, you have to use sine. So sine of 30 degrees equals opposite, which is the y force, right? Because this is Fy, the length of this side of the triangle is what the vertical component of the force is. Fy over 300, so Fy, the force of the y tension here, is sine of 30 times 300, or 300 newtons times the sine of 30. Sine of 30 is 1/2, so Fy is actually 150 newtons. So the vertical component here is positive 150 newtons for the tension. All right, and you can check this with Pythagorean's theorem. Square root of 150 squared plus 260 squared equals 300. All right. So it says, write an equation showing how the forces acting in, or the components acting in the y direction, add together. All right. Oh, I got a little ahead of myself figuring this out, actually. But we'll save it for now. So it says, total vertical direction must add up to 0. So what we do here is all the forces on this axis, and this will make sense when you think about what's going on over here, right? All of the forces on this axis must add up to 0. So I have 9 and 4 going up. Therefore, I must have a total of 13 going down. So Fn plus Fty plus the force of gravity must equal 0. All right, that's how they add together. Using the weight equation, it says, determine the force of gravity acting on the box. So why is it asking me to do that? We always have to do this. Fg equals mg. Pretty much when we do these problems, we pretty much always just find Fg right away, right in the beginning. We say Fg equals mg, so Fg equals, what was the mass of this box? 50 kilograms. 50 kilograms times g, which is 10 newtons per kilogram. Therefore, Fg has a magnitude of 500 newtons. But here's the trick. Since it's pointing down, we're going to make it negative. The force of gravity is negative 500 newtons because it's pointing down. All right? Now, let's go to part I. Using trig, determine the strength with which the mover is pulling vertically. All right, so we already did that. It's the y component of the tension. We did that using sine. Now, we're going to put it all together. How much force must the floor support to keep the forces balanced? The force the floor has to support is the normal force, all right? It's not always just equal to the weight of the object, okay? This is why this is not an action-reaction pair. The normal force does not always have to equal the force of gravity. In this case, the rope is helping the floor hold up the box, essentially. The person is helping the floor hold up the box. The normal force, we don't know what it is. It's Fn. Fty we know is positive 150 newtons. Fg we know is negative 500 newtons. Okay? So we do the math, right? Plus 150 minus 500, that's negative 350 newtons. So Fn minus 350 newtons, we just do the algebra, equals 0. The normal force only has to be 350 newtons. Move this over here, it becomes positive. Fn is positive 350 newtons. So the ground, because the rope is supporting positive 150 newtons, the ground only has to support 350 newtons, giving us a total of 500 newtons to balance out the weight of the box. Whew! You might have to watch that one a couple times. Good luck to you. This is a first stab at a whole nother level of physics here. All right, so good luck to you.